Hello, Shagath Unknown here. Welcome to another Rust coding stream here on the 28th of September 2022, local time 1744. I am safe and secure in the knowledge that I feel like I'm forgetting something and I have no idea what it is. That's going to be fun. I may have missed something in my setup. Well, there's something I know I haven't set up, but there's a reason for that. But we'll see as we go, right? I've got us a new project set up here, Coding Stream 12, Roguelike Tutorial in Rust Part 1. This is going to be many parts to get through all of this. So let's go ahead and not waste time and let's get started. I'll go ahead and say last time we finished up the Rltk tutorial, Roguelike tutorial in Rust plus Rltk or plus Tcod, whatever it's called. We finished that up last time. And I'm ready to move on to this one. And just from a quick kind of look at things, I haven't delved too deep into any of the lessons really, but of course I have to sneeze right as I start talking, right? I guess it like jostles something in my nose. I don't know. Give me one moment. God, that's the worst. It's like some half sneezes. It's not even like the real deal. Okay. So just from taking a look here at this, it looks like this whole, it's called section 1 because the intro is I guess the first thing here in the list, but the section 1 here, 2.1 all the way through 2.13, looks like it's going to be making a roguelike. And then everything after that is like we have some stretch goals on some different things we can do to add to the game. We have an entire section on generating maps to go into more detail. And then there's another section on making a game. So we'll see what that's all about. I haven't really delved into it too much, so we're just going to kind of let it simmer and we'll get to that eventually. One second. All right, sorry about that. Hopefully that's better. So I read this last time, but that was a separate video, separate series. It was kind of a primer for getting ready for this one. So I'm like adjusting myself here. My chair is like caught in the carpet. Alrighty, this is a cursed start. It's okay though. So that was a bit of a primer for this. So let's go ahead and read back through this again. And just to get things started here. Looks like building for the web we'll check out, see what that's about. Hello Rust is going to be pretty simple. I'm going to go through that one pretty quickly, and then we'll probably go into the entities and components. I don't know if we'll get to the map or not today. I don't want to rush this, but this first one might be just kind of skimming through a couple of the, starter things pretty quickly. So we'll see how it goes. So introduction. Roguelike tutorial in Rust. About this tutorial, it's free and open source. All code uses the MIT license, so you're free to do with it as you like. My hope is that you'll enjoy the tutorial and make great games. If you enjoy this and would like me to keep writing, please consider supporting my Patreon. And it is Black Future, it looks like. But yeah, I mean, you got the URL here, bfnightly.bracketproductions.com/chapter_0.html. You could also search for Roguelike tutorial in Rust. You'll find it. And it is Herbert Wolverson. Just want to give full credit because I am, relying on this person's work here, and I think I'm going to learn a lot from it. So anyway, They say that every year the fine fellows over at r/roguelike dev run a Tutorial Tuesdays series encouraging new programmers to join the ranks of roguelike developers. Most languages end up being represented, and this year, 2019, I decided that I'd use it as an excuse to learn Rust. I didn't really want to use Rltk, the default engine, so I created my own, Rltk. My initial entry into the series isn't very good, but I learned a lot from it, and you can find it here if you're curious. The series always points people towards an excellent series of tutorials using Python and Rltk. You can find it here. Section 1 of this tutorial mirrors the structure of this tutorial. Slight critique. Replace this with that, maybe? Section 1 of this tutorial that we're looking at now mirrors the structure of the Python tutorial and tries to take you from 0, how do I open a console to say hello Rust, to hero, equipping items to fight foes in a multi-level dungeon. I'm hoping to continue to extend the series. I also really wanted to use an entity component system. Rust has an excellent one called Spec, so I went with it. I've used ECS-based setups in previous games, so it felt natural to me to use it. It's also a cause of continual confusion on the subreddit, so hopefully this tutorial can shine some light on its benefits and why you might want to use one. I've had a blast writing this and hope to continue writing. Please feel free to contact me. I'm Rltk on Twitter. If you have any questions, ideas for improvements, or things you'd like me to add. Also, sorry about all the Patreon spam. Hopefully someone will find this sufficiently useful to feel like throwing a coffee or two my way. Take a quick look over here at the GitHub. This is Rltk, I think. Oh, it's been renamed. This is Rltk, renamed because it's increasingly finding usage outside of just roguelikes. It's also been divided into a number of crates. So the Rltk crate still works. Yeah, it preserves compatibility with all existing Rltk projects. It's just a wrapper, so that's good to know. We have a couple things here like geometry, bracket algorithm traits, color, all kinds of stuff here. Some noise, that'll be cool for random stuff. Pathfinding, we got A star, Dijkstra, okay. Definitely remember Dijkstra's algorithm. Well, I remember using it. I don't fully remember how it works, but you could use it for shortest path. And then you could basically run Dijkstra's algorithm in a loop to do what's called all pair shortest paths. But we're not going to talk about that. That's graph theory kind of stuff. All right, so the first thing we're going to do is look at building for the web. I have no idea if this is going to be like WebGL stuff or what. Oh, it's really short. Or not WebGL, yeah, WebAssembly. It's right there. WASM. About this tutorial, okay, we're not going to read that every time. So WebAssembly is a cool system that lets you run compiled code from non-web-based languages and run them in the browser. It comes with a few limitations. You are sandboxed, so you can't access much in the way of files on the user's computer. Threads work differently in WASM, so normal multi-threading code may not work without help. Your rendering backend is also going to be OpenGL, at least until WebGL is finished. I haven't written code to access files from the web, so you have to embed your resources. The tutorial chapters do this with the various Rltk embedded resource calls. At the very least, you need to use include bytes or similar to store the resource in the executable, or you can help me write a file reader. WebAssembly is the tool used to make the playable chapter demos work in your browser. Okay, so that's what he's using so that we can actually like play it here in the browser, but we're not really gonna worry about that probably for what we're doing, but it's good to know, and we'll just follow along with this real quick. So building for the web. The process for making a WebAssembly version of your game is a little more involved than I'd like, but it works. I typically throw it into a batch file or shell script to automate the process. By the way, this being a few years out of date now, I think it's probably a lot simpler. I've seen some examples, and it seems like it can be pretty simple these days. The tools you need. First of all, Rust needs to have the target installed to handle compilation to WebAssembly. Target name is WASM32 unknown, assuming that you set up Rust with RustUp. You can install it by this RustUp target add. You also need a tool called WASM BindGen. This is a pretty impressive tool that can scan your WebAssembly and build the bits and pieces needed to make the code run on the web. I use the command line version. There are ways to integrate it into your system. Hopefully that'll be the topic of a future chapter. You can install the tool with cargo install WASM BindGen CLI. You'll have to reinstall WASM BindGen when you update your Rust tool chain. So to compile for WASM, I recommend performing a release build. Debug versions can be huge and nobody wants to wait while an enormous program downloads. We'll navigate to the root, we'll do cargo build release target WASM 32 unknown. And the first time you do it, it'll take a while. It has to recompile the libraries you're using for WebAssembly. And it's going to make a target WASM 32 unknown release folder. And then we're going to have your project.d, your project.wasm. Okay. And then determine where to put the files. For the sake of simplicity, I'm going to use a target folder named wasm. You can use whatever you like, but you'll need to change the names and the rest of these instructions. Create the folder inside your root project folder. For example, make dir wasm. Symbol web files. Now you need to use okay, so you compile it and then you use bindgen to build the web infrastructure required to integrate with the browser. And it's this big old long command here. Well, it's really just long because it's doing a bunch of path there. Target wasm release project. If you look inside the wasm folder, you see two files, a JavaScript and a wasm file. I typically rename these files to my blob.js and my blob.bg.wasm. You don't have to do that, but it lets me use the same template HTML each time. And it would make a boilerplate HTML in your wasm folder. It's literally just going to be some HTML, which it's a script. We load and we do the wasm bindgen on that blob file that he's talking about. Okay. And then you host it, and you can't run it from a local file source. You need to put it into a web server and run it from there. If you have web hosting, copy your wasm folder to wherever you want it. You can then open the web server URL in a browser and your game runs. If you don't have web hosting, you'll need to install a local web server and serve it from there. So you can run like I don't know, like a Tomcat or something simple. But I don't think we're going to need to do that. But it's just cool to kind of read over. Honestly, like he says, it's more involved than he would like, but it's not that bad. To get it running, to like write a game and then get it running in your browser that easily, it seems pretty cool to me. So I'd love to integrate this into Cargo Web or similar to provide a simple process for compiling and serving your games. Haven't made this work yet. If anyone would like to help, please head over to my GitHub and get in touch. Cool. All right, that's a little primer there. 1 second. Hello, Rust. This tutorial is primarily about learning to make roguelikes and by extension, other games. But it should also help you get used to Rust and Rltk. The roguelike toolkit will be used to provide input-output. Even if you don't want to use Rust, my hope is that you can benefit from the structure, ideas, and general game development advice. So this is key. And this is what I want to go into this with keeping in mind. Just because this is a roguelike tutorial doesn't mean you're stuck making a roguelike. What I will note is here on the left, we can see BSP. That's binary space partitioning. That was used in Doom. That was actually a major technique in Doom that was huge for the way, if I remember correctly, it was huge for basically calling what needed to be drawn and what didn't need to be drawn, how they could figure out what was visible and what wasn't visible. I believe that's how it was used in Doom. These are real techniques that are not only going to be used for roguelikes. And another way to also think about it is if you have an algorithm that does something in 2D, like generates a map or something, you can add another layer to that. You might have the algorithm generate a 2D map of rooms, and then you might add extra information on top of that to add like a 3D layer. Or you might even just use that 2D map to then build a 3D map from and say, okay, well, we have a room here. So now we plop some walls on that or whatever. Or I mean, I guess you probably already have your walls if you're doing a map gen, but then it's like plop some furniture and stuff in there, and you can give models to those things and you can turn it into something 3D. I mean, really data is data, right? And how you use that data is up to you. So I think there are a lot of options that you have. By looking at these algorithms, you can then say, oh, well, just because it's using a roguelike here and it's all ASCII based stuff, I mean, think about it. Like in a roguelike, each spot, each little tile that you move through, well, what if you now decided, okay, each tile, each character is now a 1 square meter tile, basically a 1 square meter block, right? And then instead of being an ASCII character, you put a texture on that 1 square meter block. right? You're kind of building out something a little more graphical. I mean, that's the idea of like a tile set, right? And then maybe you have like a zoomable camera and stuff. Like you could turn this into something more than just a roguelike. And that's not to say roguelikes aren't great. I love roguelikes. But the point is, if you're trying to say, oh, well, how's this going to help me with like, I want to make a game with like normal graphics and stuff. This still works, right? It's code is code. It's only going to do what you tell it to. So if you tell it to render characters, it will. If you tell it to interpret that data that you generate as a 3D environment somehow, then it's going to work, right? It's just all of how you use that data. So keep that in mind. And that's why it says here, by extension, roguelikes, and by extension, other games, because these are going to be legitimate techniques. Keep that in mind. So then this section, I'm probably going to go through fairly quickly because every single coding stream I do is a Rust coding stream. I've coded much more complex things like the little macro input runner and stuff, and the alarm, which I still haven't finished. But I've coded much more complex things, and you know, my objective on what I'm doing is not so much about teaching Rust from square one, but I still think it'll be worth just kind of going through this first chapter here, this first lesson here, but we won't spend a lot of time on it. So, question here, why Rust? Well, it first appeared in 2010, but has only relatively recently hit stable status. Again, this was written in 2019. Rust 1.0, I think, was 2015. So we're coming up on almost 10 years now. That is, code you write is pretty unlikely to stop working when the language changes now. Development is very much ongoing, with whole new sections of the language, such as the asynchronous system, still appearing and stabilizing. Again, this is a little bit outdated. Async await is actually stable now. This tutorial will stay away from the bleeding edge of development. It should be stable. Rust was designed to be a better systems language, that is, low level like C++, but with far fewer opportunities to shoot yourself in the foot. A focus on avoiding the many gotchas that make C++ development difficult, and a massive focus on memory and thread safety. It's designed to be really difficult to write a program that corrupts its memory or suffers from race conditions. It's not impossible, but you have to try. It is rapidly gaining traction, with everyone from Mozilla to Microsoft showing interest, and an ever-expanding number of tools being written in it. And just to give an update, again, this was 2019 when this seems to have been written. Yes, Microsoft has an official Rust crate, or an official Windows crate for Rust to give access to the Windows API. Amazon uses it. Dropbox uses it. Cloudflare uses it. A lot of big companies use it. The Linux kernel, I was under the impression it already made its way to the Linux kernel, but I guess not. But I think now it's, as of just a week or two ago, it was official that it is going to be coming to the Linux kernel now. So this starts a very long and slow process where maybe a lot of code in the Linux kernel can be rewritten in Rust, and new things that are added to the Linux kernel can be written in Rust. So that's going to be a huge factor for the language. Like, it is very well represented and well utilized language in the industry. Rust is also designed to have a better ecosystem than C++. Like, anything with an ecosystem is better. C++ doesn't really have one per se, but whatever. Cargo provides a complete. So what I'll say by that is, like, C++ ecosystems are typically added after the fact, right? So we see VC, PKG, and Conan mentioned there. CMake, a lot of that stuff is added after the fact, whereas Cargo is something that was, you know, integrated with the language, like it was built up with the language. So Cargo is like way better. I think, you know, it's even something you run into with a lot of Java stuff like Gradle and Maven and all that. And what's another one? I feel like I've dealt with another one. I can't remember what it was, but I feel like I've dealt with another one in some language at work one time that was terrible because it was like just slapped on as an afterthought, you know, by some third party or something. It was not fun to work with. I will say, as much as I've grown to not be much of a fan of Python, pip is pretty nice for Python, but that's all a sidetrack. So let's just start this paragraph over with. Rust is also designed to have a better ecosystem than C++. Cargo provides a complete package manager. So do VCPKG, Conan, etc. in C++ land, but Cargo is well integrated. A complete build system similar to CMake, Make, Meson, I don't know what that is, etc., but standardized. It doesn't run on as many platforms as C or C++, but the list is ever growing. I tried Rust after urging from friends and found that while it doesn't replace C++ in my daily toolbox, there are times that it really helped get a project out of the door. Its syntax takes a bit of getting used to, but it really does drop in nicely to existing infrastructure. I guess I'm doing all right, Tusk. I had a terrible headache earlier. It is gone now, I think. It seems to be gone now, so that's good. I'm tired, but I'm always tired. That's just how it is. Those work days in the office, they get me. It wouldn't bother me if I didn't have to drive an hour to get there and back. All right, let's move on. I don't know what detective Conan you're talking about, but I know about the barbarian. I don't know a detective one though. Learning Rust. Again, we're gonna go through this maybe a little bit faster. I'm not gonna, if there's code examples, I'm not gonna go through everything because I already know this. Maybe looking at some of my previous coding streams, which are on YouTube, would be helpful, I think. But I'm also still thinking of doing like proper, like well-produced lessons and stuff, like completely offline, producing actual lessons from the vein of computer science, but using Rust as the learning language, the teaching language rather. So we'll see how that works out. Anyway, learning Rust. If you've used other programming languages, then there's a lot of help available. The Rust Programming Language book provides an excellent top-down introduction to the language. Learn Rust by examples, closer to my preferred way of learning. I'm already experienced in a number of languages, providing common usage examples for most of the topics you are likely to encounter. 24 Days of Rust provides a somewhat web-focused 24-day course on learning Rust, and Rust's ownership model for JavaScript developers should be helpful if you're coming from a JavaScript or another very high-level language. If you find that you need something that isn't there, it's quite likely that someone has either written a crate package in every other language, but Cargo deals with crates to help. Once you have a working environment, you can type Cargo search my term to look for crates that help. You can also head to crates.io to see a full list of crates that are on offer in Cargo, complete with documentation and examples. If you're completely new to programming, then a piece of bad news. Rust is a relatively young language, so there isn't a lot of learn programming from scratch with Rust material out there yet. Maybe that's what I do. You may find it easier to start. I literally just said that that's something I want to do. Except mine's not about learn programming, it's computer science, but to do computer science, you also learn programming. So I want to go another like layer above just programming. You may find it easier to start with a higher level language and then move down closer to the metal, as it were, to Rust. The tutorials/guides linked above should get you started if you decide to take the plunge, however. Nice. Nice, Tusk. Getting Rust. On most common platforms, Rust Up is enough to get you a working Rust toolchain. On Windows, it's easy enough to download. It's an easy download, and you get a working Rust environment when it's done. On Unix-derived systems such as Linux and OS X, it provides some command line instructions to install the environment. Once it's installed, verify that it's working by typing cargo version on your command line. You should see something like cargo, stuff we already have set up on my end, so we're just going to kind of go through pretty quickly. Getting comfortable with a development environment. You want to make a directory slash folder for your development work, and they have here, this is arbitrary, set yours up how you want, but that's personal choice. It can really be anywhere you like. You'll also want a text editor. I'm a fan of Visual Studio Code, but you can use whatever you are comfortable with. If you do use VS Code, I recommend the following extensions. Better Toml, got it. C uses the C++ debugger system to debug Rust code. I do not have that, but I have an LLVM debugger that you can use, but you like never need to debug Rust code. So if it comes into play, we'll look into it. Rust RLS, not the fastest, but thorough syntax highlighting and error checking as you go. Now that's actually not the case anymore. Again, this is outdated at this point. RLS, this Rust RLS used to be the case, and I think it was official, but now we have moved over officially to Rust Analyzer. So if we look at Rust Analyzer, I think it's officially the new Rust linter and everything. We'll say Rust Analyzer official. That's not what I want. I think just a couple months ago, I don't really know what I would look for. I don't know what I'd look for, but I think just a couple of months ago, they, I'm going to open this up. That'll be fun. I'll follow that. Just a couple of months ago, like they basically sunset the old Rust RLS, and now it's all Rust Analyzer. So just a heads up, if you're looking at this in 2022 or beyond, unless it makes another change in the future, Rust Analyzer is what you want. Once you've picked your environment, open up an editor and navigate to your new folder. In VS Code, we do the open folder. All right, creating a project. So now that you're in your chosen folder, you want to open a terminal or console window there. In VS Code, it's terminal, new terminal. Otherwise, open a command line as normal and CD to your folder. Rust has a built-in package manager called Cargo. Cargo can make project templates for you. So to create your new project, type cargo init hello Rust. After a moment, a new folder has appeared in your project titled Hello Rust. It'll contain the following files and directories. So that works. I do it a little bit differently. I do cargo new and then the name of my project. So then it'll make a folder called project name, and it'll have all the stuff inside of it like this. You could also do cargo, I think it's cargo new dash lib or dash lib if you want to make a library. I don't do that very often, but I think we're going to end up doing that here. So we'll get to that at some point though. Anyway, so we have the Git Ignore. Yeah, we have Git Ignore if you're using Git, so you won't accidentally put files into the Git repository that don't need to be there. We have main.rs, which is our Hello World program. And we have cargo.toml, which is like defining our project and how it should be built, all our dependencies, all that fun stuff. So quick Rust introduction, the anatomy of Hello World. The auto-generated main.rs file looks like this. We have a main function with a print line and Hello World inside of it. If you've used other programming languages, this should look somewhat familiar, but the syntax and keywords are probably different. Rust started out as a mashup between ML, which means meta language, and C, with the intent to create a flexible systems language, meaning you can write bare metal code for your CPU without needing a virtual machine like Java or C# do. Along the way, it inherited a lot of syntax from the two languages. I found the syntax looked awful for the first week of using it, and came quite naturally after that. Just like a human language, it takes a while for your brain to key into the syntax and layout. So what does all this mean? What does this all mean? Fn is Rust's keyword for function. In JavaScript or Java, this would read function main. In C, it would read void main, even though main is meant to return an int in C. In C, yeah, C is weird, right? So like C, you're kind of supposed to return an int, but you can also do void main, and it just like, it's fine. In C#, it would be static void main. Main is the name of the function. In this case, the name is a special case. The operating system needs to know what to run first when it loads a program into memory, and Rust will do the extra work to mark main as the first function. You generally need a main function if you want your program to do anything, unless you're making a library, a collection of functions for other programs to use. The empty parentheses is the function arguments or parameters. In this case, there aren't any, so we just use empty opening and closing parentheses. The curly brace indicates the start of a block. In this case, the block is the body of the function. Everything within the curly braces is the content of the function, instructions for it to run and turn. Blocks also denote scope, so anything you declare inside the function has its access limited to that function. In other words, if you make a variable inside a function called cheese, it won't be visible from inside a function called mouse, and vice versa. There are ways around this, and we'll cover them as we build our game. Printline is a macro. You can tell Rust macros because they have an exclamation mark after their name. You can learn all about macros here. For now, you just need to know that they are special functions that are parsed into other code during compilation. Printing to the screen can be quite complicated. You might want to say more than hello world, and the printline macro covers a lot of formatting cases. If you're familiar with C++, it's equivalent to standard format. Most languages have their own string formatting system, and since programmers tend to have to output a lot of text. The final curly brace closes the block started in line 4. Started in number 4, not line 4. Started in 4. So we do cargo run, and then we'll get a hello world in the terminal. Well, it's not exactly what I have. I have a slightly modified hello world, a slightly modified main, where I spun up a logger, and I'm using the anyhow crate as well. My main is actually returning something slightly different. My main returns a result, which is just like an empty, the unit, is it called the unit tuple? I think, or the unit type. I think that's what it's called, the unit type. Just an empty tuple. And in a failure case, it's an anyhow error. So basically anything that, implements that trait. We spin up a logger, and then I use log info to say hello world and goodbye world. And then we succeeded, so we return OK at the end of main, and everything is good. And we see down here in the terminal, we get a hello. Excuse me, we get a hello and a goodbye. Sorry about that. Random hiccups. Okay. So useful cargo commands. Cargo is quite the tool. You can learn a bit about it from the Learn Rust book and everything about it from the cargo book if you're interested. You'll be interacting with the cargo a lot while you work in Rust. If you initialize your program with cargo init, your program is a cargo crate. Compilation, testing, running, updating, cargo can help you with all of it. It even sets up Git for you by default. You may find the following cargo features handy. We can do cargo init to create a new project. That's what you use to make the Hello World program. If you really don't want to be using Git, you can type cargo init --VCS none, and then the project name. Cargo build downloads all dependencies for a project and compiles them, then compiles your program. It doesn't actually run your program, but this is a good way to quickly find compiler errors. Cargo update will fetch new versions of the crates you listed in your cargo.toml file. We'll see this below. Cargo clean can be used to delete all the intermediate work files for your project, freeing up a bunch of disk space. They will automatically download and recompile the next time you run or build your project. Occasionally, a cargo clean can help when things aren't working properly, particularly IDE integration. One moment, I think I heard something. All right, sorry about that. I have some stuff being delivered over the next couple of days, and I thought I heard something at the door. I didn't expect anything right now, but I thought I heard something at the door. So anyway, cargo clean is good. Occasionally it'll help when things aren't working properly, particularly with IDE integration. Cargo verify project will tell you if the cargo settings are correct. Cargo install can be used to install programs via cargo. It's helpful for installing tools that you need. Cargo also supports extensions, that is, plugins that make it do even more. There are some that you may find particularly useful. Cargo can reformat all your source code to look like standard Rust from the Rust manuals. You need to type rust up component add rust format once to install the tool. After that's done, you can type cargo format to format your code at any time. If you'd like to work with the MD book format used for this book, Cargo can help with that too. Just once, you need to run cargo install MD book to add the tools to your system. After that, MD book build will build a book project. MD book init will make a new one, and MD book serve will give you a local web server to view your work. You can learn all about MD book on their documentation page. So MD book, I think, is this format of this tutorial where we have this introduction thing here on the side. We can go back and forth between the sections like this. A lot of Rust tutorials and stuff use this, and I mean, like, it's very standard. A lot of Rust tutorials or like documentation and stuff use this. I never knew where they were making it from, so that's cool to know it's MD book. Cool. I'll look into that later. That could be really helpful. You know, if I'm going to make these lessons that I'm talking about, I might take advantage of that. Making a new project. Let's modify the newly created Hello World project to make use of Rltk, the roguelike toolkit. I think I already did this, but so in cargo.toml, the auto-generated cargo file looks like this. We have some stuff. And then go ahead and make sure your name is correct. Next, we're going to ask, you know what, I'll do it. I'll do it. Authors. Cool. Now we have a name. Oh, oops, I didn't click over and show. It's such a simple thing. I just added the authors line. It wasn't here before. Authors. Shoggothanoon. All right, so next we're going to ask Cargo to use Rltk, the roguelike toolkit library. Rust makes this very easy. Adjust the dependency section to look like this. We have Rltk with the version of 0.8.0, and if you take a look there, I already have it. I did that as just a little prep thing beforehand. We're telling it that the package is named Rltk and is available in Cargo, so we just have to give it a version. You can do Cargo search Rltk to see the latest version at any time, or go to the crate webpage. It's a good idea to occasionally run Cargo update. This will update the libraries used by your program. Hello Rust Rltk styles. So go ahead and replace the contents of main with, we got a little bit of code here. This is a bit of a hello world, hello Rust as they say, where they just give you some code and then they're going to explain how it works. So if I did that right, you were looking at my code right now. Correctamundo. Okay. So what we're going to need is we're going to need an empty struct called state, and we're going to impl game state, which is going to bring that into scope. So we have a use game state up there. So that means it's a trait. We're going to impl that for our state empty struct, which really just means we just need a thing to implement this trait on to be able to run some kind of a game. Rltk. No, that's not what I want. All right, we're gonna put that and then see if I can, yeah, import it. Okay, you're gonna make me do the thing. All right, I'm gonna have to manually do it. I was trying to get it to be nice. All right, so the trait game state requires us to implement tick. So we implement it on your state struct so the engine knows what to call on each tick. That's really all it says here. And what we're going to do is do context.ctx.cls, which is a clear screen, I assume. And then ctx.print 1 hello Rust world. And in main, I'm going to leave the existing stuff. Use Rltk builder. We're going to make a context from the builder. Simple 80 by 50. So we're making an 80 by 50 window. With title. Roguelike tutorial. Build. And so we might need to swap out, yeah, we might need to swap out this anyhow trait, unfortunately. So instead of doing this here, we'll say unwrap. And instead of that, it just returns the Rltk B error. Now, what I would prefer to do is essentially implement that trait, the anyhow trait, for these errors as a way to allow it to work with that existing structure. But it's okay. It looks like returning okay is acceptable, though. So we'll build And we'll let GS equal state. And then Rltk main loop, context, context, and GS. And right there. So main loop returns one of those B errors, a B result, which matches this B error. Okay. Yeah, I see, because there's all this result stuff going on here. Okay. We got our own kind of weird type going on here, but it's okay. We can deal with it. And then click back over here. So let's break down what's happening real quick. We need Rltk and the game state. We make an empty struct called state, which just allows us to impl the game state trait for it. And then we need to make the tick function for that. All we're doing is what I presume is a clear screen and a print. The print's pretty obvious. And then we need to use an Rltk builder to set up a window, a simple 80 by 50 console with a title roguelike tutorial, and then we build it. And then we use that thing we just built, that context, in the main loop along with the game state. And then I think both of these are what's being referenced here in the tick trait, or in the tick function on this trait. Pretty sure that's what's happening. So it says we need to also make a folder called resources. Rltk needs a few files to run, and this is where we put them. Download resources.zip and unzip it into this folder. Be careful to have resources /backing.fs, etc., and not resources/backing. Okay. FS as in F sharp. What is FS? Let's find out. Let me download this. So let me go ahead and make a folder, resources, and whoops. Let me just open that in Explorer. And I'm gonna, if you just watch on the left pane there, all this is about to be dropped right in there. Because I know you can't see everything I'm doing, literally unzipping into it. Boom. I wonder if that's just some F sharp or something. Oh no, these are shaders, okay. I was like, what else is FS? Yeah, it's a shader. Okay. That's cool. Alrighty. So we got the resources, and we save and go back to the terminal, cargo run, and I'm greeted with the console. Okay, so this is one thing that I did not get set up beforehand. Oops. I did not get this set up beforehand, so I'm gonna have to capture this window. So let's take a look at it. Let me do a cargo run and see if it works. It does work. So now what I'm gonna do here is say development window capture. Where is it? Boom. There's our window. We got it working. And just to prove it, we can come down here and say in the context.print, potatoes are a balanced part of a nutritious health shake. We should get that printing now. Yeah. But it does nothing. The window does nothing. It's like useless right now. But hey, we got a window going. No pain so far, right? So back here. If you're new to Rust, you're probably wondering what exactly the Hello Rust code does and why it's there. So we'll take a moment to go through it. This is going to be a little unfortunate because, like, when we talk about the first line, we can't see the code. I'd like to be able to bounce back and forth a little bit more effectively, but I take it that, you know, if you were following along with this, you have the code as well. You can see this, and you can maybe look at the code as I read these, as I describe these. So the first line is equivalent to C++'s include or C#'s using. It simply tells the compiler that we're going to require Rltk and game state types from the namespace Rltk. You used to need an additional extern crate line here, but the most recent version of Rust can now figure it out for you. With struct state, we are creating a new structure. Structures are like records in Pascal or classes in many other languages. You can store a bunch of data inside them, and you can also attach methods or functions to them. In this case, we don't actually need any data. We just need a place to attach code. If you'd like to learn more about structs, this is the Rust book chapter on the topic. Very helpful. Part 3, or number 3, impl game state for state is quite a mouthful. But we're telling Rust that our state structure implements the trait game state. Traits are like interfaces or base classes in other languages. They set up a structure for you to implement in your own code, which can then interact with the library that provides them, without that library having to know anything else about your code. In this case, game state is a trait provided by Rltk. Rltk requires that you have one. It uses it to call into your program on each frame. You can learn about traits in this chapter of the Rust book. 4. fntick and mute self, ctx, and mute Rltk is a function definition. We're inside the trait implementation scope, so we're implementing this function for the trait. So it has to match the type required by the trait. Functions are a basic building block of Rust. I recommend the Rust book chapter on the topic. In this case, fntick means make a function called tick. It's called tick because it ticks with each frame that is rendered. It's common in game programming to refer to each iteration as a tick. You might hear the phrase game ticks. 2, it doesn't end with an arrow type, so it's equivalent to a void function in C. It doesn't return any data once called. The parameters can also benefit from a little explanation. And mute self means this function requires access to the parent structure and may change it. The mute is short for mutable, meaning it can change variables inside the structure, state. You can also have functions in a structure that just have and self, meaning we can see the content of the structure but can't change it. If you omit the end self altogether, the function can't see the structure at all, but can now be called as if the structure was a namespace. You see this a lot with functions called new. They make a new copy of the structure for you. 4. ctx and mute Rltk means pass in a variable called ctx. Ctx is an abbreviation for context. The colon indicates that we're specifying what type of variable it must be. The ampersand means pass a reference, which is a pointer to an existing copy of the variable. The variable isn't copied. You are working on the version that was passed in. If you make a change, you are changing the original. The Rust book explains this better than I can. And 6, mute once again indicates that this is a mutable reference. You're allowed to make changes to the context. And 7, finally, Rltk is the type of the variable you are receiving. In this case, it's a struct defined inside the Rltk library that provides various things you can do to the screen. All right, so that was all our function definition, the fntick and mute self ctx and mute Rltk. Now moving on, ctx.cls says call the CLS function provided by the variable. ctx.cls is a common abbreviation for clear the screen. We're telling our context that it should clear the virtual terminal. It's a good idea to do this at the beginning of a frame unless you specifically don't want to. 6. ctx.print11 hello Rust world is asking the context to print hello Rust world at the location 11. 7. Now we get to the fn main. Every program has a main function. It tells the operating system where to start the program. 8. Use Rltk builder, and then let context equal Rltk builder, simple 8050, with tile roguelike tutorial, and .build. Question mark. That's an example of calling a function from inside a struct, where that struct doesn't take a self function. In other languages, this would be called a constructor. We're calling the function simple 8050, which is a builder provided by Rltk to make a terminal 80 characters wide by 50 characters high. The window title is Roguelike Tutorial. Let gs equal state is an example of a variable assignment. See the Rust book. We're making a new variable called GS, short for game state, and setting it to be a copy of the state struct we defined above. And lastly, Rltk main loop context GS calls into the Rltk namespace, activating a function called main loop. It needs both the context and the game state we made earlier, so we pass those along. Rltk tries to take some of the complexity of running a GUI/game application away and provides this wrapper. The function now takes control over the program and will call your tick function every time the program ticks, that is, finishes one cycle and moves to the next. This can happen 60 or more times per second. Hopefully that made some sense. I want to call attention to one thing because I don't feel like it was broken down much here. This was described as kind of as like a constructor, and to an extent, yes, but this is using what was mentioned here as the builder. This is actually using the builder pattern, which is not really a constructor per se, but at some point it does have to build out this context under the hood. So what kind of type are we getting back from it? We're getting a B term back from this Rltk builder. So I don't know exactly what a B term is. We'd have to look a little bit more into, okay, go to B term. A B term context. So it's some kind of a terminal. We have the width and the height of pixels. We have an FPS, frame times, mouse positions, left click, shift, control, alt. We have all kinds of information attached to it, basically. But I don't exactly know all of what a B term is. But basically, we are not actually calling like a constructor on B term. We're using a builder pattern. And then somewhere in this, when we call build, it actually goes and makes a B term struct, which is what that feeds back. It takes all the with this and with that, because we could stack other things. Like I could say .with advanced input, whatever that is, or I could say .with fancy console, whatever that is. Looks like you could do OpenGL. We could do with, there's all kinds of other things we could do, right? With font, with VSync, with sprite sheets, we could do all kinds of stuff. And basically every time you call one of these .with, it keeps stacking this information into the builder. And then when you do .build, that gets packed into the struct, into the B term struct, right? Hopefully that makes sense, but it's not like we're calling a B term constructor explicitly. The Rltk builder is the one that's kind of doing that implicitly. I just want to hopefully make that clear, because it's not exactly the same thing. Maybe I'm getting caught up on details, but it's fun. All right. So playing with the tutorials. You'd probably like to play with the tutorial code without having to type it all in. Well, the good news is that's up on GitHub for your perusal. You need to have Git installed. Rust should have helped you with that. Choose where you would like to have the tutorials and open a terminal. Okay. I am going to hold off on doing that. Yeah, I'm going to hold off on doing that because I don't really want to. We're going to be writing it. We're going to be typing it and going along with it. This is like, you can do that if you want, right? You cd into a directory and you git clone it, and then you got a bunch of things here. We got book, we got all the chapters and everything, right? So the book folder contains the source code for this book. You can ignore it unless you feel like correcting my spelling. Each chapter's example code is contained in chapter XY name folders. For example, chapter 01 Hello Rust. The source folder contains a simple script to remind you to change to a chapter folder before running anything. Right, so you cd into chapter 01 or chapter 02 and then run it. Resources have the contents of the zip file you downloaded for this example. All the chapter folders are pre-configured to use this. Cargo.tom will set up to include all the tutorials as workspace entries. They share dependencies so it won't eat your whole drive, re-downloading everything each time you use it. And to run an example, open your terminal and then cd into one of the chapters and do a cargo run. If you're using VS Code, you can instead use File Open Folder to open the whole directory you checked out. Using the inbuilt terminal, you can simply cd to each example and cargo run it. Accessing tutorial source code, and there's a link to it. github.com/the/rust roguelike tutorial. All one word there, rust roguelike tutorial. Updating the tutorial. I update this tutorial a lot, adding chapters, fixing issues, etc. You will periodically want to open the tutorial directory and type git pull. This tells Git, the source control manager, to go to the GitHub repository and look for what's new. It will then download everything that has changed, and you once again have up-to-date tutorials. I want to check something. Dark City, Dark Plaza. So over here in what we're looking at, it looks like there may be one section beyond this Dark Elf City, so we may go to that point. So it looks like it is still being updated. Actually, we could go back to the GitHub there. I should leave it open. 3 months ago is pretty recent. Dark Plaza. 10 months ago. It's not as recent as I thought. But we have the Dark City, which is the Dark Elf City. And then Dark Plaza, I guess, is the extra bit. Okay. Cool. Updating your project. You may find that Rltk RS or another package is updated, and you'd like the latest version. From your projects folder, you can type cargo update to update everything. You could type cargo update dry run to see what it would look like to update and not change anything. People update their crates a lot, so it can be a big list. I didn't know about that. Cargo update -- dry run. I do happen to know, because I have a little thing that helps me here, that there is a new version of Rltk, but I went with the existing. Oh. Why? That's not really helping. It's not really telling me what would change. Well, if I do cargo update, it should just be the Rltk. No? Well, so the deal is, it's just that 8.1, so it's like a minor version. So I guess it doesn't regard that as worth updating. I'm not sure. Whatever. I'm not going to lose sleep over it right now. I might change it, I might not. Updating Rust itself. I don't recommend running this from inside VS Code. Actually, I want to draw attention to one thing. Normally, this is red if it's not the latest version. Like if I do 7, see, it's like, yo, 8.1 is the newest, and I would go in and do 8.1. But for some reason, when I do 8.0, it doesn't seem to want to... It's green. It seems happy. We'll go with 8.1 though, because maybe it's a bug fix or something, right? Anyway, updating Rust itself. I don't recommend running this from inside VS Code or another IDE, but if you'd like to ensure that you have the most recent release of Rust and associated tools, you can do rust up self-update. This updates the Rust update tools. I know that sounds rather recursive. You can then type rust up update, and it's all the latest version of all the tools. And then there are a number of ways to get help. You can contact Herberticus. The fine people on Reddit r/rust. Also Reddit r/roguelike dev. So there we go. And we can actually run this in the browser as an interactive thing. And oh my god, it's amazing. All right. I noticed it wasn't actually showing text, but I might not have WebGL on Brave, so I'm not gonna sweat that. All right, chapter 2. We're definitely gonna do this one. We're only an hour in. I don't know if I'm gonna do the map one today or not. I'd be pretty excited to do it, but we'll see where we're at after this. Entities and components. This one this is actually quite a bit longer than the map one too. Yeah, like twice as long. And this is one I really want to take in because I'm interested in entity component systems. We've done a couple things related to them on the stream. We used a bit of an ECS style system in the last roguelike tutorial. Before that, I did a tutorial about building an ECS from scratch. And here we're going to be using specs, if I remember correctly from the introduction chapter. And specs is a very well-known Rust crate, along with other ones like Legion. That's a Rust crate for an ECS. So there's quite a few out there, and actually, yeah, I see specs here. So we're going to see how they use specs, and we're going to learn a little bit about using it ourselves. So this chapter will introduce the entire of an entity component system, which will form the backbone of the rest of this tutorial. Rust has a very good ECS called specs, and this tutorial will show you how to use it and try to demonstrate some of the early benefits of using it. About entities and components. If you've worked on games before, you may well be used to an object-oriented design. It's very common, even in the original Python Rltk tutorial that inspired this one. There's nothing really wrong with an object-oriented design, OOP, object-oriented programming, but game developers have moved away from it, mostly because it can become quite confusing when you start to expand your game beyond your original design ideas. You've probably seen a class hierarchy such as this simplified one. A base entity, and then a monster inherits from that, and then you have two different types of monsters, a melee mob and an archer mob, and then a melee mob has a type called an orc warrior, and the archer mob has an orc archer. So, this is stuff that fairly common. So I'm going to just kind of take a little sidestep here and give some of my own thoughts on object-oriented programming, object-oriented design. Typically, a lot of us learn about that in university. What I did in university when I studied computer science, we started with C, and we did about a semester and a half in C, and then we moved to C++ as our main learning language from that point on. And that was so that we could talk about things like standard algorithms and data structures that are in the C++ standard library. So what we would do is we would learn about a data structure, and then we would write our own, and we would also use the existing data structure from the standard library to, compare and contrast how the one we wrote behaves and functions, and we could benchmark against the one from the standard library. And generally, we wouldn't expect ours to be quite as good because we were students, but that was the idea, so that we had things like lists and all that in the standard library that you don't really get in C, and like maps and all that. So the point is, though, is that when you go into C++ and you're dealing with classes, you're dealing with objects at that point, and one of the big things that comes up with objects is like inheritance and everything, and this is the whole idea of object-oriented design. And you get a lot of inheritance going on. You get, the dreaded diamond pattern of inheritance as well. Basically, it's something that makes a lot of sense to programmers, especially early on. The example is like you have a base class, which is an animal, and then you can have a dog and a cat class. And they both implement a lot of the same functions that an animal has to implement, but a dog does things differently than a cat, right? And then you could have another animal class like a hedgehog or something, right? And they run really fast. So it's like you could keep adding other classes that inherit from animal. And then, maybe you even go a level deeper and you say, oh, but I also want something to inherit from cat. Maybe we want to have two different types of cats or something, right? So you could keep going down those levels of inheritance, and this kind of class hierarchy is a very natural way to think about organizing things. It organizes things in a very human-oriented way, because that's how we like to classify things. But one of the things that was mentioned is that developers have been moving away from object-oriented design, and that's interesting because back in the day, some of the earliest games didn't really take advantage of object-oriented programming. It was around, because it's really been around for a long time, but they didn't really use it. To the best of my knowledge, it started becoming more common in the 90s when the shift to C++ for game development was happening. But, there were a lot of programmers back then that were doing C or something, and even some of them that were switching to C++ would do what they call C-style C++, just to kind of take advantage of some of the nice built-ins of C++, but they still write their code like C. But for the most part, yeah, the industry did move towards object-oriented programming. To the best of my knowledge, again, I wasn't in the industry, but it's something I'm fascinated by and I like to read about and listen to interviews and stuff. And then there was that shift towards data-oriented design. And basically, the first explanations I heard of data-oriented design talked about DICE, who makes Battlefield. And the example was like, you look at Battlefield compared to other shooters. And when you're playing online in Battlefield, it looks better than other online shooters. It has more players in the matches than other online shooters. And it runs better than other online shooters for the most part. Why? Well, one of the things that I heard was data-oriented design. And ECS, Entity Component Systems, go a lot more hand in hand with data-oriented design. And what is the point of data-oriented design? It is to actually organize your data in a way that makes sense for the computer. Maybe not as much for the human, but what it means for us as a human, as we're writing code that's in data-oriented design, it means that we have to think about things in a little bit of a different way, but it also teaches us how to think about things kind of more efficiently. Because it's like, oh, well, if we organize our stuff like this, the computer is going to be more efficient at accessing these things due to like caching or whatever. We could do like auto vectorization maybe. There's a lot of cool techniques that can come into play that allow you to basically process your data much, much faster and more efficiently. This is like the high level overview, right? And so just to go back to the ECS, I'm not saying that it is necessarily data-oriented design, but it kind of is going hand in hand with data-oriented design and really has a lot of potential if it's done right. You could do ECS poorly and you'd probably be a lot worse off than object-oriented design. But that's enough of that sidetrack. So we had our little blurb there about OOP, and we've got the class hierarchy here. So then he says, you'd probably have something more complicated than that, but it works as an illustration. Base entity would contain code or data required to appear on the map as an entity. Monster indicates that it's a bad guy. Melee mob would hold the logic for finding melee targets, closing in, and killing them. Likewise, archer mob would try to maintain the optimal range and use their ranged weapon to fire from a safe distance. The problem with the taxonomy like this is it can be restrictive, and before you know it, you're starting to write separate classes for more complicated combinations. For example, what if we come up with an orc that can do both melee and archery and may become friendly if you've completed the Friends with the Greenskins quest? You might well end up combining logic from all of them into one special case class. It works, and plenty of games have published doing just that, but what if there were an easier way? Entity component based design tries to eliminate the hierarchy and instead implement a set of components that describe what you want. An entity is a thing, anything really, an orc, a wolf, a potion, an ethereal hard drive formatting ghost, whatever you want. It's also really simple, little more than an identification number. The magic comes from entities being able to have as many components as you want to add. Components are just data grouped by whatever properties you want to give an entity. For example, you could build the same set of mobs with components position, renderable, hostile, melee AI, ranged AI, and some sort of combat stats component to tell you about their weaponry, hit points, etc. An orc warrior would need a position so you know where they are, a renderable so you know how to draw them. It's hostile so you mark it as such. Give it a melee AI and a set of game stats and you have everything you need to make it approach the player and try to hit them. An archer might be the same thing, but replacing melee AI with ranged AI. A hybrid could keep all the components, but either have both AIs or an additional one if you want custom behavior. If your orc becomes friendly, you could remove the hostile component and add a friendly one. In other words, components are just like your inheritance tree, but instead of inheriting traits, you compose them by adding components until it does what you want. This is often called composition. The S in ECS stands for systems. A system is a piece of code that gathers data from the entity/components list and does something with it. It's actually quite similar to an inheritance model, but in some ways it's backwards. For example, drawing in an OOP system is often, for each base entity, call that entity's draw command. In an ECS system, it would be get all entities with the position and a renderable component and use that data to draw them. For small games, an ECS often feels like it's adding a bit of extra typing to your code. Well, it is. You take the additional work up front to make life easier later. That's a lot to digest, so we'll look at a simple example of how an ECS can make your life a bit easier. It's important to know that ECS is just one way of handling composition. There are many others, and there really is no right answer. With a bit of searching, you can find a bunch of different ways to approach ECS. There's plenty of object-oriented approaches. There are plenty of free function approaches. They all have merit and can work for you. I've gone with the entity component approach in this book, but there are many other ways to skin the cat. As you gain experience, you'll find one that's comfortable for you. My advice, if anyone tells you that a particular method is the right one, ignore them. Programming is the art of making something that works rather than a quest for purity. So just a quick example of another one too. A number of years ago, I put together a little combat system. This was probably 2017. I put together a little combat system, and it was like text-based, but I wanted to build out like this kind of large combat system that could then later be put into a game. And I did it like very object-oriented programming. This was when I first started working in the industry, and I was using Java at my job, and I was like, maybe Java's not so bad. And I used Java to initially do it, and then I kind of got tired of Java pretty quickly. So I refactored it all into C++. And it was basically the identical class structure and everything. I just redid it in C++. Point is, what I had at that point was something along like this like inheritance hell that you kind of get into with object-oriented code. And maybe I was doing a bad job at it, but I had like an equipment class, and then equipment had, well, it's either armor or it's a weapon, right? So then the weapon class inherits from equipment, and then there are two subclasses for weapon. There's ranged and there's melee, right? And I don't remember if it went much deeper than that, but like I had an item class, right? And the item class was like, okay, actually equipment was also an item because it was like item and then equipment and then weapon and then melee weapon, right? On the other hand, there was like consumable items, and then there were different kinds of consumable items, and technically some of those consumable items were kind of like weapons because they would damage the enemy, right? So it gets really complex when you start doing that inheritance structure. I had a system that worked, and it was kind of fun to play with, but it was a real pain, and it was definitely hard to manage. And I may not have done the best job at designing it, but it was fun. I could say that much. So anyway, just another example of what you might look at when you're doing something like that. And then I had something similar for like all the for the character, for like the players, for like the what did I call it? I don't remember. Whatever it is, like the NPCs and the player, they all inherited from the same thing, but there are obviously differences. And then I did do something where the AI would take like a closure, like a Lambda function or whatever, so I could swap in different AIs and stuff. But it was it was a pain. That would be easier to do in Rust. I could say for sure it'd be easier to do in Rust, but it was, it is what it is. It got pretty difficult to manage. That's where I'll leave that. Including specs in the project. To start, we want to tell Cargo that we're going to use specs. So open Cargo, and we'll add specs and specs derive. You don't got to watch me do this. I'm going to copy paste that and just bring it right into the cargo.toml. Boom, it's in there. Now I'm getting specs that's 16.1. It's telling me there's a 18.0, 0.18.0. I'm going to leave it at 16.1 to match the tutorial. Because I don't know how much may or may not have changed. So let's just stick with what they got there. So this is pretty straightforward. We're telling Rust that we still want to use our Rltk, and we're also asking for specs. The version number is current at the time of writing. You can check for newer ones by typing cargo search specs. We're also adding specs derive, which provides some helper code to reduce the amount of boilerplate typing you have to do. Yeah, so derives will be fun, I'm sure. I think we're going to be deriving components, and yeah, I can actually see it down below already. We're going to be deriving like components and stuff rather than having to type the code out manually. We'll probably make a struct and be like, hey, this is my fighter struct, and then derive component for that, and then we can just magically use it as a component. Bet that's how it's going to work. So at the top of main, we're going to add a few lines. So we're going to do some dependencies here. Simple enough. Once again, I don't normally encourage like, you know, copy pasting stuff, but these are a couple quick dependencies. Normally I would type code and then let the IDE auto insert the dependencies. I'm just going to paste those in real quick because it's simple enough, right? But let's break down what we're actually bringing in. So we already had our Rltk and game state. We also do RGB, so some color related thing, and we do virtual key code. That's going to be for our user input. Just guessing, because that's how these things work. Specs prelude just brings in all the specs, like just the general specs stuff, basically. So a prelude is like, the way I understand it and the way I would describe it is like, it's all the basic stuff that you would generally be using for something. So if like you're bringing in chrono for time related stuff and you don't want to like have to manually import like 6 different things that like every code that uses chrono uses anyway, you just do like, you use the chrono prelude, and that's like an easier way to just quickly bring all that stuff in. That's the idea of the prelude. And then we're bringing in the comparison algorithms, or if you call them algorithms, min and max, so we can compare things. Simple. And then we're doing that specs derive component, so we're going to be able to actually do that derive. So then, and yeah, we got the Rltk ;: shorthand, and then everything in the little curly braces there are just different things that are in that Rltk namespace. So you can type Rltk console every time you want a console. It tells Rust that we'd like to just, this tells Rust that we'd like to just type console instead. I don't see console in here, but sure. Maybe that was just the example. Likewise, the use specs prelude line is there, so we aren't continually typing specs prelude world when we just want world. Old Rust required a scary looking macro use call. You don't need that anymore. You can just directly use the macro. You know, I remember that from some of the first times I started looking at Rust. I remember that. Rust has come a long way. It's much better these days. I used it first back in like 2017, and I was like, oh my God, I do not like the, like I knew there was so much hype behind Rust, but I just did not enjoy using it back in 2017. And then I came back to it in like late 2019 going into 2020. I'm like, oh my God, this is so much better now. I'm never using anything else ever. It's like a couple years makes a huge difference sometimes. Or maybe just a different mindset. Maybe it was all up here. But I do know for a fact that 2019 was another Rust version, so maybe there was something to it. So we need the derivations from specs derive component, so we add that. Yeah, use specs derive component. Defining a position component. So we're going to build a little demo that uses an ECS to put characters on the screen and move them around. A basic part of this is to define a position so that entities know where they are. We'll keep it simple. Positions are just an X and a Y coordinate on the screen. So we define a struct. These are like structs in C, records in Pascal, etc. A group of data stored together. See the Rustbook chapter on structures. Okay, it's simple enough. Struct position, X and Y. I also like that, you know, they keep bringing up Pascal. And that's something that I used a little bit in university. Not a whole lot, but Pascal is not the first language you hear a lot of people bring up. So that's kind of cool. I like that. Pascal, like Prolog, especially, you don't hear a lot of people bring up Prolog. Anyway, that's easy enough. Just a new struct with an X and a Y. Very simple. The position component has an X and a Y coordinate as 32-bit integers. Our position structure is what is known as a POD, short for plain old data. That is, it is just data and doesn't have any logic of its own. This is a common theme with pure ECS components. They are just data with no associated logic. The logic will be implemented elsewhere. There are 2 reasons to use this model. It keeps all of your code that does something in systems, that is code that runs across components and entities, and performance. It's very fast to keep all the positions next to each other in memory with no redirects. Let me repeat that. It is very fast to keep all of the positions next to each other in memory with no redirects. Okay? So if you backtrace 5-10 minutes to when I was talking about data-oriented design, this is what we're talking about. If everything is right next to each other in memory, you can maybe take advantage of things like auto vectorization or something. I don't know too much about that. I know there's a single instruction, multiple data, SIMD. There's a lot of cool stuff you can do that just super fast, super speedy. You can look at benchmarks and it's very impressive. I don't have as much experience with that as I would like, and that is something I should look into as I'm actually building my game, because performance is fun. Like you want the game to perform well, right? I want that game to play on a toaster and a pregnancy test, all right? When I make my game. At this point, you could use position S. Or are we saying we could actually like declare one? I'm not sure what. Yeah, let me just read it and we'll see where it goes. At this point, you could use position S, but there's very little to help you store them or assign them to anyone. So we'll need to tell specs that this is a. Oh, you could use positions. I see what it means. You could use them in your data or in your program. But there's very little to help you store them or assign them to anyone. So we need to tell specs that this is a component. Specs provides a lot of options for this, but we want to keep it simple. The long form with no specs derive help would look like this. So we make our struct, and then we have to implement the component trait for position. So we do impl component for position, and then we have to define the storage type. And so we say it's going to be vex storage. And I guess vex storage, I don't know if that's, I assume that's not a built-in thing. Let me see. Oops. Sorry, I know it's terrible. Hang on. Let's see if I can get vex storage to pop up. Tell me where it's from. It's specs. Yeah. So that's actually from specs. Where's it at? Specs, storage, and then storages. Oh, I'm surprised it didn't. Oh, it came in the preludes, didn't it? So, we have any storage, anti-storage, a B tree. So this is actually cool because you need to understand your data structures. Like, what is a B tree? Why would I want to use a B tree? Doesn't actually give you any info on why you would use it, but you need to understand your data structures basically to determine, okay, maybe I want this special type of storage here. Do I want a hash map? Do I want masked storage? Occupied in tree, whatever. Like, there's a lot of different options here. Not that many, I guess, but vex storage, write storage, storage with read and write access. Yeah, this is just straight up using a vector, but it's cool. I didn't know how that was going to work, so it's cool that I was like, what is vex storage? That is a specs thing. That's basically all I wanted to confirm. So yeah, we define what storage type we want to use for the trait, and we say vex storage. So that's the longhand way to do it, but we can derive it to avoid manually doing that impl. You'll probably have a lot of components by the time your game is done, so that's a lot of typing. Not only that, but it's a lot of typing the same thing over and over, with the potential to get confusing. Fortunately, specs derive provides an easier way. You can replace the previous code with derive component. So let's go ahead and derive the component. So just right above our struct, this is where you do all your derives. And I could do debug, I could do copy, I could do clone, I could do partial equal, like I could do all this, right? We're just gonna do component. So now that's implemented that trait for us, and we see one implementation and it just points to derive component, but that is implementing a trait automagically for us. And that's why we needed specs derive, so we could do that automagic work. Fun stuff. What does this do? Well, pound derive x is a macro that says, from my basic data, please derive the boilerplate needed for X. In this case, the X is a component. The macro generates the additional code for you, so you don't have to type it in for every component. It makes it nice and easy to use components. The macro use, the pound macro use specs derived component from earlier is making use of this. Derived macros are a special type of macro that implements additional functionality for a structure on your behalf, saving lots of typing. Okay, so there's a slight inconsistency here. We did not do this pound macro use thing. We just did use specs derived component, as we can see up here. Use specs derived component. But that was this comment here. Old Rust required that macro use call. So this is what it would look like, but we don't have to do that. But yeah, saves us lots of typing. It does it for us. So I guess it just assumes vector, or it figures out maybe, I don't know if it has a way to figure out depending on your data, maybe a different type. That would be odd, but maybe it's possible to use different storages in different cases. So anyway, now we can define a renderable component. A second part of putting a character on the screen is what character should we draw, and in what color? Well, to handle this, we'll create a second component, renderable. It'll contain a foreground, background, and glyph, such as to render. So we'll create a second component struct. Let's do that. And we're going to get right here. Whoops. Okay, struct renderable. And it's going to take a glyph. Glyph is a fancy word that basically means like a character. That's actually like the formal term for it, though. Glyph is the thing that shows up on screen. This G is a glyph. This L is a glyph. This Y, this T, they're all glyphs. If you ever look into like fonts and stuff, you'll see them called glyphs there. We have a foreground and a background color that we can define, or that are part of the struct. So RGB comes from Rltk, and it represents a color. That's why we have the use Rltk RGB statement. Otherwise, we'd be typing Rltk RGB every time. We're saving keystrokes. So once again, this is a plain old data structure, and we're using the derive macro to add the component storage information without having to type it all out. All right, now for worlds and registration. So now we have two component types, but that's not very useful without somewhere to put them. Specs requires that you register your components at startup. What do you register it with? A world! A world is an ECS provided by the Rust Crate specs. You can have more than one if you want, but we won't go there yet. We'll extend our state structure to have a place to store the world. All right, let's get over there and do that. So state was an empty structure, as we see here, right? And now we're going to say ECS world. And now in main, when we create the world, we'll put an ECS into it. So then we do world new, where we're actually making that. See, state is mad, so we'll say ECS world new. Whoops. I like leaving the trailing semicolons. I think other people, maybe coming from other languages, would not like it, but it's common practice in Rust, and I think it's nicer because if you add things later, you already have a, did I say trailing semicolons? Trailing colons. Not colons, commas. No wonder I was broken. Excuse me, let's try that again. I like leaving the trailing commas like they're on world, or world new, because if we add something else to state, which we probably will at some point, we already have that comma there and we can easily add another line. It's just convenience. And it's pretty common in Rust. That's just what you see in Rust code. So common, in fact, that Clippy can even tell you. If you use Clippy as your linter to come in and check for like code smells or whatever, he'll tell you. He'll be like, hey man, you should trail it with a comma. But you can also actually set Clippy to tell you that it's bad to trail if it's unneeded. So you can do both, but whatever. I think you can do both on that. Maybe I'm making something up there. Whatever. Notice that world new is another constructor. It's a method inside the world type, but without a reference to self. So it doesn't work on existing world objects. It can only make new ones. This is a pattern used everywhere in Rust, so it's a good idea to be familiar with it. The Rust book has a section on the topic. The next thing to do is to tell the ECS about the components we've created. We do this right after we create the world. So, okay, so right after we make it, we're going to register position and renderable. Okay. So let's go right here. Let me space this out a little bit too. And we're going to say gs.ecs register position. And we're going to do the same thing, but for renderable. So these are now two valid components. Also, we need to make that mutable now. If we're doing that, let's format. Okay, something was odd on the formatting, so that's good enough for now. Okay. Oh, and they actually made it, yeah, they made it mutable here, but I missed it. Okay. So what this does is tells our world to take a look at the types we're giving it and do some internal magic to create storage systems for each of them. Specs has made this easy. So long as it implements component, you can put anything you like in as a component. There it is. Creating entities. Now we've got a world that knows how to store position and renderable components. Having these components simply exist doesn't help us, beyond providing an indication of a structure. In order to use them, they need to be attached to something in the game. In the ECS world, that something is called an entity. Entities are quite simple. They are little more than an identification number, telling the ECS that an entity exists. They can have any combination of components attached to them. In this case, we're going to make an entity that knows where it is on the screen and knows how it should be represented on the screen. We can create an entity with both a renderable and a position component, like so. So let's do it. Let's do it. So we register our components, and then we're going to do gs.ecs. So we're going to get the ECS out of it, and we're going to create an entity, and it's going to be with a position. So x40 and y25. Now what this already tells me, if we look over with, we should see that it's a generic function that takes in a trait, which just has, so it'll take in a die and component, right? I assume. Yeah. Well, I don't know if that's actually I read it or not, but it's there's a type constraint here that says T has to implement component. That's the real key here. T has to implement component. So it is a generic. C has a type of T, and we just put the generic thing here to say, you know, T. And then we make that type constraint. So anything that implements component can be used here. That's the magic. And then we also want renderable. And for that, we want glyph to be Rltk to CP437. Now, I don't know what CP437 is, so we might have to look into that. But it looks like it takes a character. It's converting it to some standard that I'm not familiar with. Code page 437. Yeah, we'll have to look into that. But it's again, probably another format. What it probably is like an extended ASCII character set or something that might be used for roguelikes. I'm not sure, though. Maybe not exactly for roguelikes, but just has been adopted for roguelikes. The difference being that it might not have been created for them, right? Oh, we got a trailing comma here, nice. Okay, so we've got our code in place. So we create entity with a position with a renderable. We make it the @ sign. The foreground is yellow, the background is black, and we build it. That's it. What this does, it tells our world, ECS, and our GS, our game state, that we'd like a new entity. That entity should have a position. We've picked the middle of the console, and we'd like it to be renderable with an @ symbol in yellow on black. That's very simple. We aren't even storing the entity. We could if we wanted to. We're just telling the world that it's there. Notice that we're using an interesting layout. Lots of functions that don't end in a semicolon to separate out the end of the statement, but instead lots of dot calls to another function. This is called the builder pattern and is very common in Rust. Combining functions in this fashion is called method chaining. A method is a function inside a structure. It works because each function returns a copy of itself. So each function runs in turn, passing itself as the holder for the next method in the chain. So in this example, we start with a create entity call, which returns a new empty entity. On that entity, we call with, which attaches a component to it. That in turn returns the partially built entity, so we can call with again to add the renderable component. Finally, .build takes the assembled entity and does the hard part, actually putting together all of the disparate parts into the right parts of the ECS for you. You could easily add a bunch more entities if you want. Let's do just that. So we're going to make a loop here and just make a bunch of them. So let's go ahead and do it. For I in 0 to 10, we're going to do gs.ecs.create entity with position I times 7, y 20, with renderable, and the glyph can be, oh, I don't know how to type that. We're going to copy it. Rltk 2cp437. It's a little happy face, but I don't know how to type it, so. Those are good for NPCs. And this is going to be RGB named Rltk red. And I'm going to copy that because I'm lazy, and then because this is just going to be the same thing but black. And you can make little dudes, because that's actually a common way to represent people or NPCs or whatever. It's used like in Dwarf Fortress and stuff, even little face. All right. So yeah, we're just looping through and making 10 of them. That's all there is to it. The I component of the position is just based on, or well, the X component of the position is based on the I value from the loop. So it's going to be at 7 or it's going to be at 0 and then 7 and then 14, 21, 28, 35 and so on until you get to 9. You'll stop at 10. So you won't hit 70. You'll hit 63. This is the first time we've called a for loop in the tutorial. If you've used other programming languages, the concept will be familiar. Run the loop with I set to every value from 0 to 9. Wait, 9, you say? Well, Rust ranges are exclusive. They don't include the very last number in the range. This is for familiarity with languages like C, which normally write for I equals 0, I less than 10, plus plus I, or I plus plus, whatever. If you actually want to go all the way to the end of the range, so 0 to 10, you'd write the rather cryptic for I in 0 ... equal 10. The Rust book provides a great primer for understanding control flow in Rust. You'll notice that we're putting them at different positions, every 7 characters, 10 times. And we've changed the @ to a smiley face. 2cp437 is a helper Rltk provides to let you type/paste Unicode and get the equivalent member of the old DOS CP437 character set. You could replace the 2cp437 with a 1 for the same thing. What? Let's take a look at that real quick. Is there another function in there? Let's just call this right here Rltk . It's not a 1. I'm not sure what is meant by that. Yeah, I'm not sure. One moment. Okay. So might have to look into what is meant by that. Oh, wait. I think I know what is meant by that. Does this just return a number? Font char type. Yeah, okay. That's all it's meant. Whoops. So, I just literally replaced it with that. And it's still happy. It compiles. Carbohydrate. I saw Rayon popping in there. Rayon is a great parallel computing library for Rust. Oh, I did not mean to click that. Go away. We want to be back here. Okay, so I guess 1 in that character set is the happy face. So that's all there is. Okay, that's all there is to it. You just have to know that character set. You can find all the glyphs available here. And yes, if I zoom way in, you can see it. 1 is that happy face right there. 2 is another one. 3 is the heart. Is like 47 or 45 or no, 41 is A. I don't remember my ASCII apparently. Oh, wrong way. Good to know. Okay. So that's like everything that we can use. This is on Dwarf Fortress. This is on the Dwarf Fortress wiki. Did I not just say that they use that smiley face in Dwarf Fortress? There we go. So next, iterating entities, a generic render system. So we now have 11 entities with differing render characteristics and positions. It would be a great idea to do something with that data. In our tick function, we replace the call to draw hello Rust with the following. Let's hop over and do it. So here is our tick function. So what are we going to do? We're going to get our positions. So we're going to say let positions equal. So we're going to get this from the ECS. We're going to read storage. And we're going to basically ask for everything that, whoops. Oh, there's a freaky sound outside. Weird. I don't know what that is. Ooh, that weirded me out. Now we're going to get renderables. Read storage. Renderable. So what we've basically done here is we've told it what concrete type we want, renderable or position, and it's probably going to go use like Dyn and stuff and basically try to downcast that as a way to actually get everything that is of that type. So then we have all of the components that are position and renderable, and then we're going to join those together because to render something, we need it to be renderable and it needs to have a position, right? And it looks like they implemented some nice iterable stuff on this for us, so we can just reference it here and we slap them into this into this tuple, and we join them and we can just iterate over them. Very nice and easy. I like that. I'm curious about something, however. ctx.set position.x position.y render.fg render.bg render.glyph. What I'm curious about, and this is, I would hope, intriguing to everybody if you are following along, is what if something doesn't have a component? Right now, as we're joining this up, We know that we defined 11 things in a specific order. They all have this. They all have positions and renderable components. What if we had something in, like, what if the fifth entity in our system doesn't have one of these? Everything is now misaligned, right? Because we have, what if it doesn't have renderable, but it has a position? Well, now we have one extra position than renderable, so I don't think this would work. We need some way to actually tie them together with the entity ID or something. I'm not sure the right way to do this in specs, so I know we're going to see this. I know that's going to be a question that comes up, but that is something that's just immediately on my mind as we're doing this. Things to think about, right? So anyway, yeah, we query it. Basically, we read the storage for positions and renderables, and we do the context.set. Oh, actually, I shouldn't skip this because it's funky. We have all the positions and all the renderables. We do a .join, which I guess is similar to a zip. .join comes from specs. It creates a joined iterator, and maybe join actually does the work that I was just talking about. Maybe join makes sure that they are matching entities. So maybe that's not a problem. Go to join iter. Yields all indices, return a none for missing elements, and joining components for iteration over entities with specific components. Yeah, I think it might actually handle that for us. This is not like a built-in Rust join, because you'd use zip for that if you were trying to take two different iters and smush them together. So I think this does the work for us. We'll read on and see. So basically, we take both of these results, we join them together, we smush them together, and that gives us an iterator with positions and renders, and then we do context.set, and we have to give it an X, a Y, a foreground, a background, and a glyph. So we already have all that data in our two components there. So pretty easy, right? So what does this do? Well, I just explained, but let's get their explanation now. Let positions equal self.ecs.read storage position asks the ECS for read access to the container it is using to store position components. Likewise, we ask for read access to the renderable storage. It only makes sense to draw a character if it has both of these. You need a position to know where to draw, and renderable to know what to draw. You can learn more about these stores in the specs book. The important part is read storage. We're asking for read-only access to the structure used to store components of each type. Fortunately, specs has our back. And this is that join. So for position render in positions renderables dot join. The line says join positions and renderables, like a database join. It only returns entities that have both. Exactly. So I was right in saying I think that join handles it for us. It then uses Rust's destructuring to place each result, one result per entity that has both components. So for each iteration of the for loop, you get both components belonging to the same entity. That's enough to draw it. The join function returns an iterator. The Rust book has a great section on iterators. In C++, iterators provide a begin, next, and end function, and you can move between elements and collections with them. Rust extends the same concept, only on steroids. Just about anything can be made into an iterator if you put your mind to it. Iterators work very well with for loops. You can provide any iterator as the target in for X in iterator loops. The 0.10 we discussed earlier really is a range and offers an iterator for Rust to navigate. The other interesting thing here are the parentheses. In Rust, when you wrap variables in brackets, you're making a tuple. These are just a collection of variables grouped together, but without needing to go and make a structure just for this case. You can access them individually via numeric access, mytuple.0, mytuple.1, etc., to get to each field, or you can destructure them, like we've done there. So 1, 2 equals, well, saying that out loud doesn't help, but we can see it here. I'll highlight it just to make sure. This sets the variable ONE to 1 and the variable TWO to 2. That's what we're doing here. The join iterators returning tuples containing a position and a renderable component as .0 and .1. Since typing that's ugly and unclear, we'll destructure them into the name variables position and pos and render. This can be confusing at first, so if you're struggling, I recommend Rust by example section on tuples. If you're doing Rust programming and you're new to it, get used to using tuples because they are very much part of idiomatic Rust. They are all over. So anyway, context.set, and then we literally feed it the X and Y, the foreground, the background colors, and the glyph. So we're returning this for we're running this for every entity that has both a position and renderable component. The join method is passing us both, guaranteed to belong to that same entity. Any entities that have one or the other but not both simply won't be included in the data returned to us. Context is the instance of Rltk passed to us when tick runs. It offers a function called set that sets a single terminal character to the glyph and colors of your choice. So we pass it the data from position, the position component for that entity, and the colors/glyph from render, the renderable component for that entity. With that in place, any entity that has both a position and renderable will be rendered to the screen. You could add as many as you like and they'll render. Remove one component or the other and they won't be rendered. For example, if an item is picked up, you might remove its position component and add another indicating that it's in your backpack. More on that in later tutorials. So now we're going to have the complete rendering code, and I think we already have this all in place. Let's do a quick rundown. I'm not going to talk about every line. Let's just do a quick rundown of what's going on and skip the uses here. We derive component for a position struct as well as for a renderable struct. We have our state struct, which contains the ECS world. We implement game state for our state struct, and that's actually where we have the tick function here as part of that game state trait. And in that tick function, we just get the positions and the renderables, join them together, and we set each one, we basically set each one to the context, or in other words, like we're setting it to display in the console, in the terminal. And then in main, what do? Well, we build out a context, which is just our window, an 80 by 50 window with a title. We make our game state, which has the ECS world. We register components. We make an entity that's specifically like the player, and then we do a loop to make 10 NPC type entities with the little happy face thing. And then that's it. We do the main loop. We pass the context in the game state, and we're good to go. So yeah, let's go ahead and run and see if it works like it should. Where is cargo? There's cargo run. Too lazy to type it. There we are. That's what we expect to see. Simple enough. So I think we're going to start doing some movement in this as well, in this chapter. So that's nice. Getting right to the movement. That's one of the first things people like doing when they're making, when they're getting into game programming. How do I move a character, right? People like doing that because it feels like you've accomplished something great. So yeah, we have an example system of random movement. I think we're going to make the NPCs move. This example showed you how an ECS can get a disparate bag of entities to render. Go ahead and play around with the entity creation. You can do a lot with this. Unfortunately, it's pretty boring. Nothing's moving. So let's rectify it a bit. Then make a shooting gallery type look. First, we'll create a new component called left mover. Entities that have this component are indicating that they really like going to the left. The component definition is very simple. A component with no data like this is called a tag component. We'll put it up with our other component definitions. And then we'll have to register it as well. So we have to tell the ECS to use the type with our other register calls. So yeah, we'll make left mover, and I'll register it here for us. I'm going to copy that right there to be a little bit lazy, and we'll rename it to left mover. And then I'll copy that name. Actually, you know what's quicker? Boom. Left mover, just like that. So we've got it registered, we've got it created, very simple. Now we have to, yeah, we've done that. Now let's only make the red smiley faces left movers. So their definition grows to, okay. So we also add the with left mover. That's the only thing that's actually changing about them. So we just add yet another component to them. So right here, dot with left mover. For the tag, we have to do that. Okay, yeah. So you still have to put brackets even if it's a tag like that. All right. Notice how we've added one line with left mover. That's all it takes to add one more component to these entities, and not the yellow at. Now to actually make them move, we're going to define our first system. Systems are a way to contain entity component logic together and have them run independently. There's lots of complex flexibility available, but we're going to keep it simple. Here's everything required for our left walker system. So we're going to make another struct. So we're going to go right up here where I made left mover. We're going to say struct left walker. And it's also like a tag struct. Is that what they called it? They call it a tag component. So yeah, you wouldn't say it's a tag struct. But now we have to do this weird impl, and I can't wait to get this breakdown because we're doing lifetimes already. And I just imagine if you're new to Rust, you're like, what is this? So basically, we have to prove to the compiler that something's going to live long enough to satisfy this constraint. That's what's happening with lifetimes. And I guess it's maybe needed for the traits themselves, for the read storage and write storage. Oh, it's not systems, it's system. Why did I put aspect? Oh, because I tried to save. Not all things are implemented, that's fine. So we're gonna, don't go there. So we're gonna need run. It takes immutable reference to self. Lefty, mute position. This is an interesting thing to see in a parameter. I've done this before, but you're passing in like two things basically. System data, I think, is going to contain this left mover and position. Yeah, no, it is. We're defining it here. System data is a tuple of read storage with left mover and write storage with position. So, oh, right. So it's going to say like get components that have left mover and right positions. Okay. I think we're going to break it down. I'm just kind of guessing as I go. Lefty position in and lefty and mute position dot join position dot x minus equal 1 if position dot x less than 0 position dot x equals 79. What? Oh, we're wrapping. Duh. What? Okay. No, that makes sense. Cool. So we can break down what's happening here one time. Basically, we're having to implement this system trait. We're going to talk about lifetimes in a minute. I'm going to let them talk about lifetimes. I already kind of hinted a little bit at what's going on. But we define a type here called system data, local to this trait. And then we're actually saying that the input we get for this run is of type system data. That's what this is here. And then because this is a tuple, we can actually break it apart here in the function definition. So we call part of it lefty and we call part of it position. And then we smush those together with the join to make sure we get only entities that have both. And that means so any entity that has lefty and a position will move to the left. But if position.x is less than 0, we wrap it around to 79 so it goes to the other side of the screen. Now I wonder something. Position.x. Isn't there clamp? Restrict a value to a certain interval. Yeah, so you could say something like this. Position, I know. Position.x minus 1 dot clamp. I'm gonna wrap this and then you would say 079. So you could also do that, kind of one-line it. I don't know if it's inclusive or not, but you could use a clamp to do the wrapping for you. Maybe nicer, maybe not. This is more standard code, I think. This is more what you'd expect to see in something like C code. So just bring into light other options, other functions and stuff. Not that one way is necessarily better than another. This isn't as nice or simple as I'd like, but it does make sense when you understand it. Let's go through a piece at a time. So the struct left walker just defines an empty struct, somewhere to attach the logic. Impl, how do I want to say this? A, system A for left walker means we're implementing specs as system trait for our left walker structure. The A, the single quote A, are lifetime specifiers. I don't know how to like read that. Well, I'll just call that lifetime. Lifetime A are lifetime specifiers. The system is saying that the components it uses must exist long enough for the system to run. For now, it's not worth worrying too much about, but if you're interested, the Rust book can clarify a bit. Type system data is defining a type to tell specs what the system requires. In this case, read access to left mover components and write access since it updates them to position components. You can mix and match whatever you need in here, as we'll see in later chapters. fn run is the actual trait implementation required by the impl system. It takes itself and the system data we defined. The for loop is system shorthand for the same iteration we did in the rendering system. It'll run once for each entity that has both a left mover and a position. Note that we're putting an underscore before the left mover variable name. We never actually use it, we just require that the entity has one. The underscore tells Rust, we know we aren't using it, this isn't a bug, and stops it from warning us every time we compile. The meat of the loop is very simple. We subtract 1 from the position component, and if it is less than 0, we scoot back to the right of the screen. Notice that this is very similar to how we wrote the rendering code, but instead of calling into the ECS system is calling into our function/system. Let me read that again. It's very similar to how we wrote the rendering code, but instead of calling into the ECS is calling into our function/system. So we just wrote the function that's being called. That's what they mean. It can be a tough judgment call on which to use. If your system just needs data from the ECS, then a system is the right place to put it. If it also needs access to other parts of your program, it's probably better implemented on the outside calling in. Now that we've written our system, we need to be able to use it. We'll add a run systems function to our state. So we have to impl state and do run systems, okay? Let's find state up here. I'm going to say impl state run systems. And we take a mutable reference to itself. And I guess that makes sense because if we're going to be potentially modifying things in the world, then yeah, that all checks out to me. Okay. Let mute LW equal left walker. LW.run now. And I'm guessing we can do run now because it actually has, we've defined system for it. So we defined run, but this system trait probably has some other things already implemented that we don't need to manually implement. One of those being run now. If I mouse over it, it should say, yeah, it's from system. Literally runs the system now. And then self.ecs.maintain. And it takes a world. So we pass in the world to it. And then what does maintain do? Merges in the appendix, recording all the dynamically created and deleted entities in the persistent generations vector. Also removes all the abandoned components. Additionally, lazy update will be merged. Okay. We'll have to read more on that, I think. So, yeah, we just did that. I'm not going to reread it. It's relatively straightforward. Impl state means we would like to implement functionality for state. Fn run systems and mute self means we're defining a function and it needs mutable, i.e. it is allowed to change things, access to itself. This means it can access the data in its instance of state with the self keyword. Let mute lw equal left walker makes a new changeable instance of the left walker system. lw.run now and self.ecs tells the system to run and tells it how to find the ECS. Self.ecs.maintain tells specs that if any changes were queued up by the systems, they should apply to the world now. Okay, then that does make sense. So all the right stuff that was set up, like changing the values of position, I think those are the changes that we're talking about. So finally, we actually want to run our systems. In the tick function, we add self.runSystems. And do we just put that at the end, or we put, yeah, the end wouldn't make sense, but we put that right after we clear the screen. So I'm going to go ahead and do that. Okay, self.runSystems. And now we can do that because state also implements system, right? So we get that. Or no, that's the one right there. My bad. Yeah, I'm sorry. I was mixing that up with the run now. My bad. Yeah. So we get that because we made it ourselves. But all right, that should be good. Let's see. The nice thing is that this will run all systems we register into our dispatcher. So as we add more, we don't have to worry about calling them or even calling them in the right order. You still sometimes need more access than the dispatcher has. Our renderer isn't a system because it needs the context from Rltk. We'll improve that in a future chapter. So your code now looks like this. And then if you run it, we got a spoiler. Don't look. Let's run it. Let's do it. It's going to be great. Yeah. It looks way better on my main monitor than it does on the stream. It's not terrible. I think it's because it's a blown up view on the stream. This is like a fairly small console on my monitor, and it's a blown up view on the stream. So it's like they have to move further per tick. The mouse is jittering as I'm moving it around my monitor. Alrighty. We have movement. We have life. Okay. Well, we need more than that, right? We're almost done with this chapter, though. We are going to stop after this chapter. Walking a map could be a lot of fun and would be a lot of fun, but I want to take this very seriously, try to absorb this, try not to overdo it. I don't want to do like a 4.5 hour thing, like trying to cram in like just one more, just to get like, there's so much cool stuff down here, but you know, in due time. In due time. So next, moving the player. Finally, let's make the @ move with keyboard controls, so we'll know which entity is the player. We'll make a new tag component. So we're actually deriving debug as well, which is interesting. Deriving debug for a component or for a struct that has nothing in it, I've never tried. But we'll do that and we'll register the player component. So where are we at? We'll get component and we'll get debug and we'll get player. And then down here, we'll just say player. Easy enough, right? Okay, so we'll add it to the player's entity, of course, with player. Now we implement a new function, try move player. So that's what we're going to do. Let's go ahead and add it to the player first. And we're going to impl this. And we're just putting a function the top level here. So let's go ahead and make it. So it takes a delta x, a delta y. Delta, you know, if you know your math, your physics or whatever, you're used to that term where typically delta is used to mean the change in something. So delta x and delta y says how is our x and y value changing. So we're going to get ECS.write component or .write storage, and it's going to be position. So this is actually something that I'm interested in. ECS dot, so player doesn't need, oh, it is write storage. Okay, well, we'll see how that works out. I was going to say player could probably be read. So here's something I'm interested in. This is, you know, where things get genuinely interesting to me. And I wonder about the efficiency of what we're doing here. So I think storage here is not really a problem because it's probably just returning us direct access to that storage. It's not actually like doing anything yet. Where I get concerned is on join. Watch this. For player and position, we actually don't care about the player component, which is why I'm wondering why it had to be write storage. Maybe again, maybe we'll break it down. I feel like that could probably be read. We're going to get players and positions and we'll join them. Now this is where I have questions about performance. What if I have 600, what if I have 6,000 things, entities with the position component, but I've only got one player? How efficient is it to do the join? That's what I'm curious about. Now, if we exhaust all the players very quickly, if, say, it was like the first thing we found in positions, because player is typically like maybe the first thing you create. That's not bad, right? But what if for some reason player is the last position we have? Do we have to look through every single position until we find it? How do we go about matching them up? Well, no, we probably have it tied to the entity ID. There's probably an effective lookup using the ID to match between the two, I guess. So you don't have to, I guess. Okay, I guess here's my concern though. You probably have to be looking at both of them and recognize when either one empties out. Because you could just say, hey, I got this position that goes to this ID. In the players, do you have an ID? Do you have one that matches that ID, right? I don't know how easy that, it's confusing. I'm not doing a good job of explaining, but I just get concerned about like pulling in every single component when you may only need a handful, if that. In this case, we only need one, but we may have a lot of positions. That's all I'm trying to say. What if you have like, I saw something using an ECS that they made a cube out of particles and it was really dense and they actually got pretty decent performance out of it. But I wonder like, what if you had one thing in there that wasn't a part of that cube, but every single thing in that cube has a position and you need to find that one thing? Like, I don't know. It seems like it could be a little messy. I don't know. But maybe there's some, something weird just happened. Maybe there's some storage tricks with the way they're managing the vectors or something, the indices, I don't know. My street, oh. The Twitch app on my phone just died and it won't come back. Oh wait, now it's coming back. I completely closed it and tried to reopen it and it wouldn't come back. I did it a couple times, now I got it. Yeah, I use it as a stream manager that I can look at, and it just like, I'm gone, bye. Okay, so enough of that sidetrack though, being concerned about the join. Because I know it's not as big of an issue as I think it is. And the reason I say that is because if it was, hold on, 0 position, okay, yeah. If it was as big of an issue as I thought it was, then this wouldn't be as popular of a framework, right? Okay, so whichever value is smaller, okay. So we're getting the minimum between 49, which is the height of the console, and this value, which is the max between 0 and whatever this is. So what, okay, so what it's saying is this could go negative. It's a funky way to do a little bit of wrapping, I think. That's how I'm reading that. Okay. So drawing on our previous experience, we can actually let me just no, we're good. Yeah, I'll just read this. I don't need to reiterate the code. Drawing on our previous experience, we can see that this gains write access to player and position. It then joins the two, ensuring that it will only work on entities that have both component types. In this case, just the player. It then adds delta x to x and delta y to y, and does some checks to make sure you haven't tried to leave the screen. We'll add a second function to read the keyboard information provided by Rltk. So, yeah, again, so it wants the smaller value between, yeah, between the extent of the screen, like the 79 is the far edge of the screen, and you try to go to 80, it picks 79. And then this max here is basically, if you try to go below 0 and you go negative, it picks max. It picks the 0, because that's larger. So it's just a cheeky way to keep you locked into the screen. We're not wrapping. That's why I was thrown off. Okay. So we'll add a second function to read the keyboard information provided by Rltk. R.L. Stein. It's in the game. It's in the book. So we need a mutable state. It's our GS. Yeah, it's our game state. We need the context. And we're going to do player movement. Now, this is going to look a lot like what we did last time in the other roguelike tutorial. If there's no input, we do nothing. If there is, you know, first of all, I always thought you had to have commas. You totally don't. Maybe they change it at some point. You could totally still use commas after each, you know, arm of the match statement, but you don't have to. So this is going to look a lot like what we did in the other roguelike tutorial. Virtual key code left, try, move player, -1 and 0. I can't wait until we add diagonal movement. So it's left, right, up, and down. And so right is going to be a 1. And then up and down, so up is -1 and down is +1. So we are doing typical computer graphics right there. We got a match within a match. That's not terribly uncommon in Rust. I can't wait to hear their description though, because they come from a C++ background, so I like their descriptions here. There's quite a bit of functionality here we haven't seen before. The context is providing information about a key, but the user may or may not be pressing one. Rust provides a feature for this called option types. Option types have two possible values, none with no data, or some X indicating that there is data there held inside. The context provides a key variable. It is an enumeration, that is, a variable that can hold a value from a set of predefined values. In this case, keys on the keyboard. Rust enumerations are really powerful and can actually hold values as well, but we won't use that yet. So to get the data out of an option, we need to unwrap it. There's a function called unwrap, but if you call it when there isn't any data, your program will crash. So we use Rust's match command to peek inside. Matching is one of Rust's strongest benefits, and I highly recommend the Rust book chapter on it, or the Rust by Examples section if you prefer learning by examples. Question. If you're going to ignore the none, you could do an if let, right? I'm trying to get better at if let. At thinking about when to use it, right? So let me try rewriting this real quick. Match if let some key equals ctx.key. No, see, I don't know. I don't know if that would work well here. If let's cool, but it'd be like this. Expected a block. Oh wait, if let some key that's it. Match key. And you put this inside. There we go. Which one is better? I don't know. If we know we're ignoring the none case, if let's kind of nice. We don't have to put that extra thing in there. But I don't know. Like it doesn't really save us the extra level of nesting. But I do understand how I can use if let there, and I want to make more use of that in the future. So it's a thing. It's something to keep in mind, right? Let's click back over now. Where was I at? Get the data out, you call unwrap. So we use match. Matching is one of Rust's strongest benefits, and I highly recommend the Rust book chapter on it, or Rust by example if you prefer learning by examples. So we'll call match context key, and Rust expects us to provide a list of possible matches. In the case of context.key, there are only two possible values, some or none. The none empty line says match the case in which the context.key has no data and runs an empty block. Some key is the other option. There's some data, and we'll ask Rust to give it to us as a variable named key. You can name it whatever you like. Yeah, we can call it potato if we want. Some potato. We then match again, this time on the key. We have a line for each eventuality we want it to handle. Virtual key code left, try move player -1, 0, and then give it the world, or give it the ECS. Says that if key equal, that is the world, right? Says that if key equals virtual key code left, virtual key code is the name of the enumeration type, we should call our try move player function with -1 and 0. We repeat it for all four directions. And then that underscore arrow empty block is rather odd looking. Underscore means anything else. We're telling Rust that any other key code can be ignored here. Rust is rather pedantic. If you don't specify every possible enumeration, it'll give a compiler error. By including the default, we don't have to type every possible keystroke. Oh, that's so sad. I wanted to have to type every. This function takes the current game state in context, looks at the key variable in the context, and calls the appropriate move command if the relevant movement key is pressed. Lastly, we add it into tick. So player input self ctx. And I guess we could put that wherever, as long as it's before As long as it's before before we do the rendering and stuff. Here's our tick. Player input, self. What is it? Cannot borrow self as immutable. What is it? Hang on. Also borrowed as immutable. Immutable borrow occurs on the read storage there. Okay. There we go. That, yeah, that'll make it happy. Because that's a temporary borrow there. But that borrow was, yeah, that was on me. That was stupid of me. This is because I'm not used to the ECS. And I wasn't making the connection. Like, I was thinking, oh, we're doing stuff with positions and renderables. We'll do the player input after that, whatever. But I wasn't also making the connection. This is actually still using the positions and renderables as well. So what we're doing is we're taking the borrow there, and then we're doing another borrow with it. Can't do it in that order. But by doing this first, the borrow is finished, and then we can use the next borrow here. Yeah. If you run the program with cargo run, you have a keyboard controlled @ symbol while the smiley face is zoomed to the left. So let's do it. Yeah. Can't go off the screen. They're faster than me. Wonder why they're faster. I'm holding the key. I guess the polling rate. I don't know. I have a pretty good keyboard. I would assume it could. I don't know. Whatever. All right, cool. We have controls. Oh, I hit escape. That's not going to work. I have to actually close it for now. And there we see the final code for chapter 2. And actually, that's our source. Yeah. Hello, ECS. It looks a bit like this. I'm not going to go through everything here because it's going to be a lot to talk about every time if we do that. But this chapter was a lot to digest, but provides a really solid base on which to build. The great part is you've now got further than many aspiring developers. You have entities on the screen and can move around with the keyboard. That's all there is to it. And next up is going to be walking a map. So we define map tiles. We build a simple map. I think this is going to be very similar to... Oh, it starts out random tiles, I think. Yeah. And we're going to make it more interesting over time. Oh yeah, look at that. This is going to look a lot like the tutorial we just did, but that green is hurting my eyes. Stop it. Ah, man. Okay, we'll deal with it when the time comes. We're not doing this today, even though this one doesn't look terribly long. We'll probably do both of the maps and maybe the FOV next time, depending on how long they take. It doesn't look too bad. We'll see about doing all 3 of those next time. And then we'll do like monsters and damage after that, and user interface and items or something. Like, it's going to be very similar to what we just did. Again, this is kind of based off of that same tutorial, but it's a different take on it. And then we'll get to the crazier stuff after that. So I feel like I wanted to mention something and I just lost my lost the thought. Something I wanted to bring up or mention or talk about. I'm not sure anymore. Let's go back over here real quick and just run this. This is going to be the end of the coding for today, though, and I wanted to talk about something with... Oh, yeah, I wanted to talk about just some general ideas that kind of come along with game development or development in general. And, you know, hopefully this would be something that could be taken as like an inspiration if you do have aspirations for being a developer or something, you could take it as an inspiration or whatever. Like, I don't know. So I just want to kind of talk about what I mentioned earlier. We're back in 2017, right when I started working on in the industry. I built that big like combat system and everything, and started in Java. Then I quickly moved over to C++. I think I actually called it Combat Plus Plus, and it was fairly robust. Like, I actually spent a lot of time working on it, and it was one of the biggest projects I had ever built on my own time. It was purely text based, and at that point I had an idea that I might do something like, what's that game called, Sanctuary RPG or something. It's got like graphics. It's not like, it's all ASCII based, but it's got like ASCII art, like a skull will pop up and that'll be like the guy you're fighting or something, and it's animated ASCII art if I remember correctly. It's a really cool game. I thought, maybe I'll build something like that out of it and have this like, kind of text-based thing or something. It never really, I didn't really do much more once I got the combat system built, which sucks, but I always thought about re-implementing it in Rust or something maybe, once I started getting more into personal coding and projects and all that. But, I just kind of want to talk about like what, if you're new to code or if you just think you might want to write code or games or something, it can seem intimidating. But I want to say this: when I first started learning how to code, it was actually like in university. I didn't have any prior experience. So I was taking a course, and they taught us the basics. They taught us about loops, and they taught us about printing to the screen, and they taught us about reading user input and all that basic stuff, how to do math, how to do, add numbers, subtract, whatever. So I'm like, okay, you've told me everything I need to know. I can make a game now. Literally, that's what I said at that point. All I had was a bit of text, and I could add and subtract numbers and stuff. And I had only been learning code for like 2 or 3 weeks. And this was like 9 years ago now, right? But I'd only been learning code for like 2 or 3 weeks, and I went home and I started writing code. And I built a combat system back then. I had a very rudimentary menu where I would print out to the user, here's your enemy, here's how much, I don't remember if I put its health or not, but whatever, I printed out to the user, like, you're fighting a dude. What do you want to do? Press, 1 to attack, 2 to defend, which was like a really stupid command, because then they would just hit you and deal less damage, but you wouldn't do any damage to them. There was no like special AI for the enemy where they would like telegraph like, I'm gonna do a big move next turn. There was nothing like that, right? But I had random numbers, and I had the concept of like a damage system where you would deal between some values, right? And same for the enemy. They did the same kind of like random system, and defending was an option, attacking was an option. I think I had items, and I had like a healing item, and I had like a throwing star, which would do more damage or something. That's it. Like, very basic, but I had only been coding for like 2 or 3 weeks, and I built that. I didn't need anyone to tell me how to build it. This is what somebody would be doing back in the 80s, right? Like in Visual Basic or Basic or whatever back in the 80s. Kid would have their computer and they'd be writing up little games and stuff, and that's kind of how you might start. No one had to tell me that a game needs a game loop, because I just figured it out. I said, well, I need a loop to basically go back to the menu every time and ask the user to input what action they're going to take. And we have to build in like somewhere in here we're going to process like what happens with the user input, and then I actually checked the user input and made sure it was correct. And if it wasn't correct, I made them re-enter it. Like, I did some proper stuff, even though I just started coding, because I was like, oh, why not? Like, do things right. They were teaching us that stuff already. They were teaching us in C. So that's things that I was already learning anyway, was how to like do user input correctly by like checking it and making sure it was correct. And then doing the while loop, like, I forget it now because it's been a while since I've written it, but you could do the while loop like on the scanf value itself. what value it returns and stuff, just to make sure it actually scanf returned like a non-error code, and then you check the input and all that fun stuff. Whatever though, right? I'm getting too in depth on that, but the point is, I'd barely been coding, and I just started doing it. That's what's important. If you have an idea, even if it's very rudimentary, it was fun. I was proud of it. I had never coded prior to a few weeks before that, and yet I had a little mini game where you could fight some enemies, and it would just like bring in a new enemy every time you killed one. And then I actually started making, what I did was, this is again very rudimentary, but I built like a little generic table, I guess you'd call it. It was not really a proper table. It was roll a random number, and then there's a whatever chance of getting a weak enemy, a lesser chance of getting a really strong, like stupidly strong enemy or something that you're never going to beat just for fun though. And you know, so I had like different enemies that could show up and stuff, right? I don't think I had any level system or anything. That was a little bit ahead of what I wanted to do at that point, of what I felt capable of at that point. But it was fun, and I had friends play it. I was like, hey, look at this thing I wrote. You got to try it. Simple, but it was mine, and I was proud of it. I was happy to be able to make something like that. And so fast forward, you know, a few years later, and here I am. I had done a game programming course, but when I built that like big combat system out in C++, when I started my job and I was like, hey, you know what? I want to write code on my own at home because I'm going to have fun with it, and there's things I want to do. I wrote that big combat system, that Combat++ system, and it took quite a while to like dial everything in the way I wanted it to, but it had level ups. It had like interchangeable AIs and stuff with like lambdas or lambda functions or closures or whatever. You know, it had like, and the level up system, like it had actual like growth formulas that, you know, accounted for leveling up slower over time, as you kind of should in a game. And enemies also followed these kind of formulas, and you could, I think that was another thing I did with a lambda, where the functions themselves for the level up growth was a lambda that you would pass in, and that way different things could have different growth functions for how they level up and everything. I had like full stats and inventories and like everything. This is a fairly robust system. I think I still have the code somewhere, so maybe I'll revisit it one day in Rust now. But the point of that is that what I did end up building from that was basically another game, a lot like what I built all those years before, except way more robust, way more interesting and fun to play, but it didn't have any graphics or anything. It was still very hard, like very, very like text-based, like too text-based really. And that does take away from the enjoyment, the way it was designed. It was still like press 1 to do this thing, press 2 to do that thing. And there was no visualization or anything. It was like just raw text, like a raw text log. But the point is, I built that system just because I wanted to, from scratch. No one like told me like, this is how you build it. This is how you're going to use it or whatever. It was just a thing of like being inspired one day, saying it could be fun to make some combat. Let's make a combat system. And that's what you should do. Like if you're interested in code, if you're interested in game development, anything like that, and you have an idea, as long as you have enough basic knowledge to try to implement it, do it. Just try it and see where you go, because you never know what that's going to lead to. I don't know if it's Barone or Barone. He also goes by the name Concerned Ape. He's a developer of Stardew Valley. He got out of school and had trouble finding a job. Granted, he was in a lucky, fortunate situation where he didn't have to necessarily get a full-time job. I think he did work part-time, but he lived with his girlfriend at the time, who was able to support them mostly on her own, and that gave him time to work on the game. But he was having a hard time finding a job in the industry, and so what he did was said, you know what? I can pad out my resume by saying I know C sharp. I've been wanting to learn C sharp. Let me start up a little project here. That project was Stardew Valley. So he said to learn C sharp, I'm going to make a game. And that game ended up selling over 20 million copies. Now, of course, not everyone's going to sell 20 million copies of whatever they make. But the point is, he started it as a learning project, as something that he could just learn from to put on his resume, and look where it got him. So if you have any ideas, or if you're interested in anything like this, use tutorials, you know, do what you need to do what interests you, but like just start doing it, right? Get there and write some code, do something. Don't just like sit there and wait for something to drop in your lap, because it's not going to happen, right? Like nobody that ever achieved greatness did it by waiting for it to just happen. They had to put that effort in. And if you're into stuff like coding and all that, then you're already like 3 steps ahead, because now it's just applying it to whatever that thing is that you're interested in, whether it's a game, whether it's some AI, whatever it is, right? So, I mean, that's kind of my little aside. And I think I always enjoyed writing code on my own. I did write a lot of my own code when I was still in university. But I think when I did Combat++, that was my first time of like really getting into and enjoying like a larger project on my own time. And then I built some other cool stuff over the years from there. But that was the first time I really saw like, hang on, I can make some really cool stuff just on my own, just sitting down hammering out code. And now here I am years later. I never really turned any of that into any projects or whatever. And that's part of why I have this new resolve that I'm going to make a game now, like for real, for real. So anyway, I think that's enough of me rambling on, just kind of waxing philosophically or whatever. There's something weird on the chat here. Okay. Something I've never seen before. Okay. Oh my God. Okay. So that's enough of that. Enough of me rambling. I don't know if that went anywhere useful. I am tired. It's been a long day, but I'm excited to be going through this again. This is going to be similar to the last one for a bit, and then it's going to get way more in depth. It's going to be really cool. But I already like the way this is using the ECS here. I feel like I learned a lot just from this today, and I hope that that this can translate to other programs in the future. So with that said, thank you to everyone who showed up today. You know, whether you're lurking or chatting, whatever, I really appreciate it. If you are new, you want to see more of these coding streams, hit that follow button. If you want to see me do some gameplay, also hit that follow button. I do coding streams on Monday and Wednesday, and I do gameplay every other day. You know, unless I'm like feeling bad or something occasionally, I'm just not feeling good, I'll, you know, skip out. That's whatever, right? But I stream pretty much every day. Yeah, so go ahead and hit that follow button. If you're watching this in the future on YouTube, congrats on being in the future. You can do all that fun YouTube stuff. You can lick that like button. You can kick that subscribe button and notification bell. Leave me a comment. And I'll say what I've been saying. When you're following a tutorial, it's a little harder to provide constructive feedback or constructive criticism on like the code portion itself, because what is there to, like, don't go to me, this is not my code, this is the tutorial's code, right? But actually, no, it's still true though. Like maybe there's something I don't understand, or maybe there's something that, you know, that could be useful feedback. I guess you still could provide it to me, but I think it would also be useful if you think there's something really worth bringing up, you know, go to the author of this as well and make sure they're aware. But definitely any constructive feedback on like how I present this, how I go about doing this, are my asides too much rambling, whatever, let me know. I really appreciate it, because I want to, you know, make these as good as possible. I want to make sure that they are enjoyable and useful, and that people get something out of them. I know you could just as easily go watch this tutorial, or not watch, but you could just as easily go read this tutorial on your own. What I'm doing here is some people learn better by like kind of getting the demonstration, getting the live demo like this, having someone kind of speaking. There's different ways that people learn. Some people can't look at like just a wall of text tutorial and just like be able to follow along with it. So that's why I do these right now. That's why I'm doing these tutorials that are not my own, because I think it would help people, and it's a chance for me to maybe learn some new concepts as well. Using specs here has really been fun so far. We'll see how it plays out for the rest of the tutorial. So with that said, until next time, where I guess today's Wednesday, so tomorrow I will be back with more Crackdown, probably beating that game tomorrow. So until then, have a good day, have a good night, whatever it is, wherever you're at, and take it easy.
Hail to the king, baby. Let's rock.